after lunch. So I see people are still coming because it's quite a challenge to get in that speed, in that time lunch, but great that you're here. One announcement up front. We have in this session only 3 papers. If you rely on the paper program, that's outdated. The online program is already updated. The second talk, Smooth Moves, has been moved to tomorrow morning to the 9 o'clock session because the authors and presenters are still on the plane. So there was a problem with the flight. So we will move the third and fourth talk 20 minutes to the front. The others know it as well. And so we have 3 talks, and with the first talk, we have Mohamed presenting EyeScout, active eye tracking for position and movement-independent gaze interaction with large public displays. And this is joint work from the Ludwig Maximilian Universities in Munich and the Max Planck Institute. And my name is Albrecht Schmidt, and funnily, I just moved to that institution a few weeks ago, so I'm quite curious.
Thanks for the introduction, Albert. So hi everyone, my name is Mohamed. I'm a PhD student at the University of Munich. It's a pleasure to present this work today. So I'm presenting on behalf of the co-authors, Axel Hoesl, Alexander Klimczak, Martin Reiss, and my supervisors, Florian, who is here, and Andreas from Max Planck Institute. All right, so we've already had eye tracking and gaze interaction for a pretty long time, like 30 years or so. And however, most of the research that has been done in eye tracking has focused on desktop scenarios or cases where you have small displays. So in these scenarios, you're expecting most of the time that the user is not moving a lot. The user is stationary most of the time and interacting for a long period of time. However, in this project here, we focus on large public displays. So actually, why is this different? Now, if you imagine that you have a large display and you want to use one of these commercial eye trackers or just a regular camera to do eye tracking or gaze interaction, the first problem you come across is that people could be approaching from different positions around the display. So it's not like there is a fixed position that is intuitive for people to go there. So you have to either guide people to stand at a certain position where the eye tracker could detect their faces, or you need to somehow, get them to go there. And also you have cases where people would be interacting with large displays while walking. So the question is, how can you enable eye tracking and gaze interaction for these cases where you have large displays, where you need to be flexible to different positions and flexible to the user's movement? So as I said, the usual way is to ask people to go to the eye tracker. So you place the eye tracker somewhere, ask people to go there. And instead of doing that, we thought that maybe we should move the eye tracker to the user. So we did this through our system, which we call EyeScout. So basically, we mounted an eye tracker on a rail system, and we use a Kinect on the other side of the room to detect where the user is, and we accordingly move the eye tracker to follow the user as he interacts while moving, and also to simply place the eye tracker wherever the user approaches. So we focus on 2 scenarios here, a scenario where a user walks to a random position, then interacts, and a scenario where the user walks and interacts while walking. So why would this be useful? You can think of the displays that we often find in airports, and we've got in the airports usually these moving walkways or like horizontal escalators, and you've got displays on your sides usually, advertisements or digital displays. And if you want to track the user's eyes as the user stands on these moving walkways, you can actually use a similar system where the eye tracker moves along the moving walkway. Also, if you go to, so this is a picture of Quebec City, so there is this Observatoire de la Capitale, my French sucks, so from which you can see the city, and you can imagine that you can have an eye tracker at such an observation tower. So simply you walk to a position in the observation tower, you look at the landmark, and the eye tracker would come, and then the system would tell you what you're looking at and describe the scene for you. We are also starting to see more of these cylindrical displays where people could interact with a display, with a cylindrical display from different positions around it. And you can also imagine having a similar system surrounding the display and moving the eye tracker depending on the user's position. So actually, why do we work on public displays? I'll start talking about how we came into this idea. So we are starting to see a higher adoption of large public displays. So not just in research, but also in in industry and in research. So, for example, you've got this big display in NASA. And as I said earlier, like, although we have eye tracking on such public displays, the idea of allowing gaze interaction on large displays hasn't been explored a lot before. And the reason is that you've got these special situations where people could be interacting from different positions and while walking. So as I said earlier, people usually try to guide people to the so-called sweet spot. So that's the position from which you can interact with the display. So if you have an eye tracker mounted at the display, you usually want the user to stand right in front of it. So one way was to, that was presented in UIST 2 years ago, is to guide people through showing cues on the screen to implicitly guide them to stand in the right position. And another way is to show the users instructions on where to stand and how to align their face. However, although this is okay for cases where you have a smaller display because it's actually intuitive to go and stand like in the center of the display, with larger displays it could disrupt the interaction process and could make the interaction not smooth enough. So the way we built this system is that we use the rail system that carries a carriage. The carriage carries the eye tracker. And we use a Kinect on the other side of the room to detect where the user is and accordingly place the eye tracker. Of course, the Kinect could be replaced with any kind of motion sensing device. And I'll speak in more details now about how we actually implemented this system. So as I said, we support 2 interaction modes. So one of them is walk, then interact. So you walk to a random position and then interact. And one of them is walk and interact. So this means actually interacting while moving. Now the system looks as follows. That's like a top view. So we have a body tracker, which in our case is a Kinect. The eye tracker is mounted on a carriage, and the following process takes place. So first, once we detect a body, there's a software component which computes where the user is and accordingly how much the carriage should move. It communicates this information to a microcontroller, which in turn instructs the rail system to move the carriage to the user so that the eye tracker would detect the eyes. As long as the user's eyes are detected, the system stays in place. If the eyes are no longer detected, we go through this whole process again. And this also allows people to interact while they are moving, the same concept. Now, to build this, we used a carriage and a rail, and we drilled some holes into the rails to get the wires to go through. We 3D printed this holder, and we drilled a hole at the bottom to mount it on the carriage. If you're interested in the detailed technical implementation, I'll be happy to share with you a technical report with more details. So just get in touch with me, and I'll be happy to share that. We used a motor and a stepper driver. So the stepper driver converts the digital signals to something that the motor could understand. We also used an Arduino. And of course, all of these parts are upgradable, so you can always use a more advanced or a faster motor. You can use a different controller other than the Arduino. We connected everything, and yeah, we also had these safety measures. So we had some switches at the sides of the rail to make sure that the carriage does not walk out of the rail. And yeah, then we conducted a user study in order to see how people really interact with their eyes while they're moving. So we evaluated the 2 scenarios that I spoke about. In one scenario, the user had to walk to a random position in front of the display, and they would have to then select something with their eyes. So we showed 3 moving objects, 2 gray objects and 1 red object. The user had to select the red one, and if they select any of the gray ones, it would be counted as an error. And in the other scenario of walk and interact, they had to do the same thing while walking along the display. So we used the pursuits method to interact via eye gaze. So the pursuits method, basically, it's an eye tracking, or it's a gaze interaction technique where you can select objects, moving objects with your eyes. The nice thing about it is that it doesn't require calibrating the eye tracker. So basically, you show the user moving objects, and then you compare the movements of the user's eyes to the movements of these objects to know which object the user is looking at. And yeah, as I said, the nice thing is that it doesn't require calibration, and it's also robust to noisy gaze data. So in the first scenario, they had to do 3 selections. And in the second scenario, they had to do as much selections as possible at 3 different speeds. So the user had to walk at different speeds. And this was our way to find if people are okay with faster speeds of moving and interacting or selecting via gaze while moving. So we recruited 26 participants, 11 of them were females, and we measured the error rate and the selection time. So when looking at the error rate, we found that actually the error rates do not change much throughout the conditions. So we actually found that the higher the speed, the more likely people will do some errors. However, the difference is not significantly different. So this means that people are more likely to do more errors when they are walking much faster. And for the selection time, we didn't find much differences also, except that in general, selecting objects while you are walking takes more time compared to selecting objects when stationary. And the reason is that since we are using this pursuits method, the way it works is that you try to achieve a certain correlation between the eye movements and the movements of the objects shown on the screen. And to reach this threshold, you usually need more time when you're walking, because as you walk, your head bobs up and down, and this distorts the gaze data a bit. We also collected subjective feedback from the participants. So we asked them about the perceived precision of the selection and also about the perceived easiness of the selection. So for precision, we didn't find a lot of differences, but for easiness, we found that people preferred selections while stationary and while moving on lower speeds compared to faster speeds. So as I said, the system could be actually upgraded in many ways. So one way is that you can actually conceal the rail. So you can imagine having a display and the rail actually behind a wall or behind a frame with a small hole that shows so that the eye tracker could see the eyes. So you could actually conceal the rail so that it wouldn't also distract the user. You can also upgrade the motor to support faster speeds or slower speeds if you like. You can use different motion sensors. So in our case, we use the Kinect 1. You could also track the entire room. So you can put the Kinect in different positions in the room. Also, in our case, when we had participants that are taller or shorter, we would then ask them to either step back in case they are taller so that the eye tracker would see their eyes. And if they were shorter, they would have to approach the display a bit. And we showed like cues, we showed some text prompts on the screen to guide them to do that. But a future system could also pan and tilt the eye tracker in order to adapt to these situations. And of course, although we used pursuits, we could also use different eye tracking techniques. So we can use gestures, for example. So we always recommend whenever there is so much dynamics while interacting, it's better to use something that is robust to calibration errors. So for example, using gestures or using pursuits would be a good approach. There are also several methods introduced in research. For example, there was a paper at CAI called iGrip where they used an eye movement type called optokinetic nystagmus, and that's actually very good, very robust against calibration errors as well. And actually, a limitation of our system is that we support a single user at the moment, and that's something for future work that we could think about ways to support multiple users. So the main take-home messages from here is that first, so the method that we use here, it's called active eye tracking. So actually moving the eye tracker depending on the user or adjusting the system depending on the user's position is a form of active eye tracking. So we think it's a really promising direction for gaze-based interaction with large displays. So if we compare the results of our study to previous work where people were first guided to position themselves in front of the eye tracker and then took the time to align their faces and so on, we would find that that kickstarting the gaze interaction process using EyeScout is 62 to 87% faster. So it's actually a huge improvement. And we also, using the system, we were able to extend the sweet spot to a sweet line. So the sweet spot when interacting with a display is like the best spot from which you can interact with the display. So in that case, if you have a stationary eye tracker in front of the display, the sweet spot would be the point in front of the eye tracker. However, using EyeScout, then we have some sort of a sweet line, so there is a bigger range of area where you can interact from. And finally, we found that gaze interaction while moving is feasible, and this was the first time to have eye tracking or gaze interaction while you're moving. However, it's also less accurate and requires more time compared to when the user is stationary. So yeah, that's all. I'm looking forward to your questions.
So if you have a question, please use the microphone and state who you are.
Hi, Andy Wilson from Microsoft. Thanks for the talk. It occurs to me that you could have calibrated the rail against the geometry of the display, the physical display, and then when you got an eye gaze point from your eye tracker, you can then relate that directly to the geometry of your display.
Okay. Yeah. So,
right, and
yeah,
you did not do that,
possible.
right? You didn't do that.
So you mean to locate where exactly on the screen the user is looking, right?
Yes.
Yeah.
Well, you need to know precisely where the eye tracker is, probably in 3D.
Yeah, it's possible to do that. Yeah, so we didn't do that here, but we used the calibration-free technique, so we really don't need to know where exactly the user is looking on the screen. We just compare the eye movements.
I get that, but I'm curious. I mean, I think that's a nice observation, but it also would have been nice to actually assess kind of the baseline accuracy if you had just followed through with that and actually got the 3D geometry and sort of done sort of I would, in my opinion, sort of the obvious thing.
Yeah. I agree that's something that's interesting to do. So we haven't done that, but that would be a good direction for future work.
Okay, thank you.
Yeah, thanks.
Hi, Steve Fonder, Columbia University. So you have a really interesting trade-off here between one eye tracker and a rail that needs to not nip people's fingers and motors that need to pull things back and forth along it, and the fact that with one single one going back and forth, if two people want to look, then unless they're walking together, they can't look at the same time. And I mean, it would seem to me that since eye trackers are just cameras and diodes, and cameras are getting cheaper and cheaper, have you thought about the alternative of just put a bunch of really inexpensive eye trackers, into something which could be a rail like that, which wouldn't have any moving parts, and then you could have multiple people looking rather than just a single person without the moving parts?
Yeah, that's a very good idea, and so definitely having multiple eye trackers would be also a good option. However, you would have to take care of handing over from one eye tracker to another, which is also a complicated problem on its own. But definitely, it's also another approach to achieve the same thing. Yeah.
Okay, thank you.
Hello, I'm Preeti from McGill. And my question is, you stated the application of eye tracker in the airport, where a person is walking and it's tracking the path. What if there are so many people walking in front of the eye tracker? So how is this applicable at that time?
So at the moment we support a single user. So this means that if there are several people, it's difficult to detect their eye gaze using the current system. But what you could do, we use the commercial eye tracker, which is built for a single user. However, you can use a regular camera, and then you can build your own eye tracking approach, and then you can support multiple users. So this would be an option, and of course, you could also consider having multiple rails to support multiple users, and kind of have several carriages moving back and forth to support as much users as possible. So this could also be a direction for future work.